Everybody, and thank you for joining us for a discussion on the Stibnite Gold Project's tailings storage facility, hosted by Perpetua Resources. I'm Shelly Bennett, the marketing manager over here at Perpetua, and I will be your moderator today. We'll have a Q&A session at the end of the presentation, but please feel free to submit your questions anytime during this presentation by clicking on the Q&A box at the bottom of your Zoom screen and putting in your question. I'd like to introduce our speaker today, Jean Bosley, our senior civil engineer. Jean, I'll go ahead and hand it over to you to get us started.
Hey, thank you, Shelly. Yeah, just briefly about me, I'm a senior civil engineer at Perpetua Resources. Been on staff here since 2016 and involved in the project since 2013. And I manage the tailings facility design, which I don't so much design it as manage the consultants that are the consultant experts that are doing the design. So with that, I'll just jump right in here. Brief little outline here is I'll give you the quick Stibnite project overview. I don't plan to dwell on that. I assume anyone here for this level of detail is at least a little familiar with the project site. Go through first because I don't assume most folks know what tailings really are. Outside of a small piece of the industry, no one really does. So I'll go through just really what's tailings management about and what really are tailings, and how we get to where we are now, which is a pretty advanced design. How do we understand tailings and a site, and how do we design that facility and manage it throughout its life, and what our design really is. And I will hit that as I go. This presentation, for those of you I think on here who have seen it before, has been reorganized a little, in that I'll hit the Stibnite aspects as I go in some cases, so as not to have to save it all to the end. I think that'll give you a little better connection to the information and hopefully flow a little better. So with that, here's just where the project is: Central Idaho, Salmon River Mountains, east of Cascade and McCall. It's a bit of a way in there via some really forest roads. So it's about 37 miles from pavement, I think, and in the mountains. And that has some consequences for construction season and design that I'll get into as I go through some of the tailings design considerations. The other thing about the site is it's been mined for 100 or so years. That's left a lot of legacies. It's been off and on mined too. So mined back in the war years, the World War II, Korean War, that's the large piece of the legacy. And then it was mined in the 70s through 90s with heap leach operations, which are another set. And the tailings facility that we propose will touch on both of those and remedy a couple of those. I won't go through all these. You've probably seen this before, but the main one is the one on the red outlined one on the upper left. The tailings is spent ore, so tailings from the World War II, Korean War era are placed in Meadow Creek Valley. Those were then overdumped by spent heap leach ore in the 1980s. And that deposit sits there to this day. And that deposit is on the site of our tailings facility in Buttress. And so that's an opportunity to reuse and recycle and reprocess some of that material and store it properly. And I'll get into the detail of that here a little farther down the line. So what this is about, of course, is risk management in tailings. And to give you a little brief one on that is, first of all, what are tailings? Okay, that's what's left over after one processes ore. So, in our case, gold, antimony, silver are extracted. What's left over really is just ground up rocks mixed in water. And that presents a management challenge, because you've got ground up rocks that it's mud essentially, and the water may or may not be nice water because it's processing water. So that presents some management challenges, and that's what we have to manage throughout the life cycle of the facility. And what that involves is, first of all, who's doing it? What's the team like? What's the site like? I went over a little bit of that. We're in the mountains, but there'll be more. And then what is your design throughout your life cycle? What sort of facility do you build? And then you've got to execute on all those steps from construction onward through closure. And we'll hit all these in turn as we go through our presentation today. And then when I talk risk, what do I mean? Well, some folks will say risk means what's the bad thing that could happen? Well, not really. Risk, when we talk in these terms, is about what could happen and how likely it is to happen. Multiply those together, that's risk. The bad thing is consequences. The likelihood is the likelihood, multiply, and that's risk. So a very unlikely but very bad thing, still not a risk maybe one wants to take. A very likely but inconsequential thing is maybe not what you want. What you want is you want your risks to be scaled where you're at the not very consequential nor very likely. That's where you want to be in the green boxes here. You don't want to be in the red box out here. And what I'll describe is how do we get to green on the risks that we do have that we can't reduce the consequences of, we reduce their likelihood. And of course, what we're trying to do here as a team is get these risks minimized, get into the green boxes on this chart here. And lots of ways exist to do that. Not all of them what we might do here, but there's lots of ways to do it. And the industry does it a lot of ways and does it well in a lot of places. And some of those, one of your first choices or early choices is, well, what are you going to, where will you put your tailings to contain them? Again, largely tailings are going to be something that at least starts out runny and therefore needs a hole to put it in. And well, that can be a pit, that's done. It can work well if the geologic containment is right. It can be a lake, that's done, and nothing we would propose. And it could be the least of all that we would not propose is discharge the stream, but those have been done. Where we are and where most of the industry is retain them with an embankment, often lined. And that's what we propose. And again, a widespread practice in the industry with a good record of success. Do we line it? Well, in our case, of course, but that's not always the case. Will be fully synthetic line, just like the one on the right. In fact, very similar as far as what the liner is. The one on the left is actually lined naturally. That site happens to be blessed with very good quality clay in the impoundment and did not require a liner to keep water leakage to a minimum. Some facilities don't require a liner simply because the tailings are relatively benign. That's not always the case with precious metals, but you see that in copper and some other base metals. Another big consideration, we'll detail this later, but we'll climate and topography. Left-hand side is one extreme. That's a flat topography. Almost that whole facility is contained by a dam. That's called a paddock configuration. And that's up in Canada. The one on the right, that's the Andes, but a cold, high, and dry part of the Andes. And that's a cross valley embankment with a considerable catchment reporting to it. The one on the left, the catchment is the facility itself. There's no valley that you've dammed. You're building what's also termed a ring dike. Not what we have here. We're closer to the climate on the left and closer to the topography on the right at our site. Next, move on to team and execution, and we won't dwell on those long because it's pretty straightforward. Again, in lots of facilities, lots of companies have these arranged different ways, right? Who's your internal team? Do you have an internal team or do you farm it all out to consultants? Externally, well, who are they, consultants-wise? What is your regulatory structure? I mean, regulations differ vastly between Central America and the US or Africa or many places that mining occurs. Do you have an independent review team? And how good are they? Not all facilities have them. These days, most do or are headed that direction. And then how long's the team been together? And as far as our project goes, we have more of an internal team than many would at our stage in the project. We have a couple of tailings experts here on our internal team. We've got industry-leading external consultants and third-party reviewers. We, of course, are regulated and subject to US regulation and several layers of it because you've got your NEPA analysis, which is why probably most of you are here, but we have state and federal regulatory oversight here as well. Again, several layers of regulation and rather conservative design standards that come out of those regulations. And then our team continuity, we've been all around on the project, working on this tailings facility at this site since 2013, some before that, but the core team's been around for that long. And then as far as construction management, this one is another one where you've got to execute the plan. However good your design team was, if the execution's poor, then you've got problems. And there are a lot of ways to execute. Our case, construction execution, there can be owner built, there can be contractor built. Some dams are entirely built by the owner with the mine fleet. Some are entirely built by specialty contractors. Ours will be a blend. Our bulk earthworks will be our mine fleet, and then the special stuff like liner and the really detailed work will be contractors. Management team, of course, we'll be using third-party construction managers and experienced ones at that, yet to be selected, of course, because of where we are in the project. Instrumentation, you want to look at a dam, make sure it's performing as expected, right? Our end will be on the extensive end. We'll be monitoring the water balance, tailings consolidation, the geotechnical stability of the dam and the surrounding landforms. So we'll be on the extensive side there. And then reviews, I've mentioned, we've got a third-party review team. We expect their involvement to continue. And of course, we expect our regulators to continue paying attention to the project. It will be regulated as a regulated dam in Idaho, so the Division of Water Resources will be out there for that. And then we're other regulations as well that I'll get to in a bit. And then if we have any questions that popped up, Shelley, I'm happy to start knocking them down now if they're relevant to what I just covered, so I don't have to backtrack.
No problem. We don't have any that have popped up yet.
Okay. All right. So onward into the deeper dive. We'll go through a bit here, of course, our site characteristics and what considerations in the design that leads to. First off, here's your general list, right? What sort of containment will you have? What are your design criteria? What does that embankment look like? Rock fill, is it earth fill? Does it have filters and drains? What are your tailings like? There's a wide range, of course. And what's your hazard classification? And that's driven by the consequences, not the risk that I alluded to earlier. Hazard classification is all about what would happen, not about how likely it is, and how big is the dam. And the combination of those two give you your design criteria under Idaho rule, as well as really any state rule in the US. And then hydrology, how wet is it? When is it wet? To go from wet to dry. You're all familiar with the mountains in Idaho, all those things. And before I leave this slide, this the one on the right here, this image, this is a picture of your typical upstream and downstream and centerline construction. The important thing to understand with tailings facilities is they're not built all at once for the full life of mine. They're built to start to handle 1, 2, 3, whatever years of production. And then they're raised either continuously or at discrete intervals every year or 2 or 3 to keep up, to keep ahead of production. They're not built to their full, in our case, close to 15 years of production. You don't build a 15-year dam in day one. You build a 3-year dam and you raise it every 3-ish in our case. Well, how one raises it has a great deal of impact on the stability of that structure, long-term and short-term. And there's really 3 key ways to do it: is upstream, downstream, and centerline, with centerline just being a blend of the 2. Upstream, you of course are raising a dam where part of the new raise sits upon tailings as well as on old dam. Downstream, you're raising it in a way that the crest moves downstream and that the new dam either sits on old dam, which is compacted, or sits on the foundation, but never sits on tailings. And that's where we will be here for our proposed dam, is the downstream method, which all else equal is more stable, particularly in a seismic situation. And then location, well, where does one put your tailings facility? There aren't that many choices in a given site. You need to have enough room for the tailings you anticipate producing. So tiny, steep side drainages don't generally lend themselves to good tailing sites, because you might have as much size in the dam as the actual volume of tailings you're storing behind the dam. And so you go through a process where you look at where are the pits. The pits, of course, are fixed because that's your resource. But where do you put your development rock? Where do you put your mill? Where do you put your tailings facility? And you circle round and round with different alternatives until you arrive at where the best one was. This image to the right is our alternatives study from back in the PEA in 2012. And you see one of those is with the square around it. That's the one we've selected. The one east of that is called Blowout Creek, which is not desirable because it's the site of a prior dam failure, hence its name, and doesn't lend itself to buttressing because it's in a hanging valley. The one to the north is Fiddle. Fiddle that would be a precedent-setting dam height in that steep valley to contain the tailings we need to contain there. And then the one to the east is actually another NEPA alternative, which was second best, but has some serious flaws, one of which is a very large landslide that you can see aimed at its abutment. Here's another view of the site with the selected site on it again. And the color here is new and old disturbance, or new and our proposed disturbance. So the hatched part is legacy disturbance from 100 years of activity out here, and the pink and hatched is overlay of our new with the old, and then the unhatched lighter pink is really our disturbance that's outside of old. So about 45% of our disturbance is on old. That site to the east is on entirely new disturbance if the facility would have gone there. And it's in a relatively pristine watershed. The only human impacts up there, pretty much some road building and forest fires, which are human or not, but that's really the impacts up in that East Fork watershed where the other TSF would have been. And again, also a very large landslide there. So the winning site was really the one that we picked in our alternatives analysis. And it's got some advantages of restoration as well, because it intersects the spent ore and legacy tailings that lie in that drainage and give us a chance to pick them up, reuse them, and reprocess them. And here this is the picture of that being in place. The gray underneath is the tailings from the 1930s through 50s, and the brown being placed on top is ongoing in the 1980s of ore that had been leached and then rinsed and then trucked away from the leach pad and dumped in this location. And our plan there is, the spent ore will make good construction material as long as you keep it away from water. So that would be placed high and dry underneath our liner of our facility. And then the tailings would be reprocessed, and they would end up mixed with our tailings from the project in our TSF. Anything so far, Shelley?
Sorry about that. Nope, we're good. Keep
Nope.
going.
Okay. Well, onward. So some key site characteristics, and all these photos are our site really, is, speaking, and I won't dwell on the rest of the site, but specific to tailings and the buttress is, well, what's the foundation? Can you put a dam on it? Will the foundation fail? That's an important thing to know for sure. And then what can you build the dam out of? And it's not just dam fill, right? One needs drain rock, one needs riprap for diversions, and how much of it is there? Fortunately, I guess, are relatively blessed on both counts. We've got, of course, glacials and glacial fluvial materials in the valley bottoms, and rock really on the sides of the hillsides. Our dams going right up against rock at either abutment. And so we have a variety of materials to select from. We don't have a lot of trouble making them. We'll have to screen to get things like drain rock. And then, of course, we're an open pit operation. So the bulk of the fill will just come from the pits, which is, that is the typical case anywhere you have open pit and need a tailings facility. Bulk of that fill is coming from the pits. In our case, again, we're blessed. It's rock fill. It tends to be very stable once in place. And then as far as the foundation, that's what we've been studying for all these years. And it's about 8 years of work. I haven't done anything last year, but about 8 years of work, almost 100 holes related to just the tailings facility and the buttress over a number of drilling methods, and then a whole lot of lab work and modeling that followed. So we feel we have pretty well understood foundation conditions here for the tailings facility. And then seismic, which is another one where we've done the site-specific work. We did one in 2013, right out of the gate, And I got the final for review today of the updates. We're not expecting a lot of change here, but the site seismicity is, we have it. We're not just in the high seismic zone, but we're just outside it. But it's pretty well understood. And I should note, the earthquake we just had gave us a shake out at Stibnite, the Stanley earthquake, but that's a sixth of our design event. So that earthquake was in the context of dam design, inconsequential, wouldn't have moved a rock. And then the other thing, of course, we have some topographic challenges here. Again, mercifully, not so much at the TSF site. The landslide avalanche hazard is more of a concern with our present access road, as some of you have probably seen in the news. And that's part of why we want a different access road that's again, under analysis right now in NEPA. And then, of course, climate. And these are the big ones for us, right? Is what's the climate? What's the hydrogeology and hydrology? Where's the water? Any mine site, right? There's always more water than you want when you don't want it, and not enough when you do. And we're not immune to that. We're generally on the site on the wetter side of more than we want in the spring, but pretty well manageable. I mean, we're seasonally wet. It's snowy. But that means reliable snowmelt runoff and a snowmelt dominated streamflow regime, which is a little easier to at least predict than some others. And we've got 39 years of record at one of the gauges on site. So we have a pretty good handle on the surface water scenario up here. The alluvial groundwater is another one, right? We don't have a lot of water at bedrock because we're in the mountains. It's granite mostly. Most of the water's in the alluvium. And that's compartmentalized because sometimes it's 200 feet thick and sometimes it's 2 feet thick. And our TSF catchments, as those go, are small. The one we picked is about 6 square miles, and they ranged from 2 to 10 in drainage area that we needed to divert. And where that's all leads, right? If you've got water, you've got to manage water. We'll manage water all these ways, right? We need a water supply from mill water. That's separate from the tailings question, but that water is what ends up in the tailings. I mean, we need to recycle water. No one just pours water into their tailings facility, leaves it there. We want that back. We recycle it. We use it in ore processing, and we reuse it over and over. We pump a lot of water in circles with reclaim going back to the mill and tailings slurry going out. And we recover as much of it as we can and reuse it. And then, a couple of ways, right? One is a barge. You'll see that. That's the upper image on the right. The lower one is a decant tower. We're going to have a barge, but we won't need to do that. And then, aside from our recycled process water, one has to deal with the water surrounding your facility. Well, we'll need under drains, keep groundwater from affecting the liner, and we'll have surface diversions to keep the creeks out of the facility and route them around and keep the clean water clean. And again, we'll need all these things. Most sites do. I mean, even a dry site has enough water to need most of these elements. And then how does one size them? Well, a key one is what's your water balance and what's your return period storms? What's your 100-year storm? All that kind of stuff. It's just typical hydrologic analysis like one would do with any dam. The added thing is the tailings component of the water balance. And we'll get to that in a little bit down the line here. And here's where we start with that, right? Is, tailings physical characteristics matter a great deal in how one designs the facility and what your water recovery looks like. And then their chemical characteristics, that's your environmental risk, right? And both of those matter. And both of those are something we spend a decent amount of money testing. Here's just some examples. Some of these are general curves, and the one above is actually from the gradation curve is from our site, and some of the testing apparatus that we use. And where this all leads, though, physically in tailings facility, the biggest one that matters here for this design and for most, right, is consolidation. And when I say that, what I mean is that, the tailings arrive at the facility as a slurry. In our case, half water, half solids by weight, give or take. And when they land there, some of the water will separate, but a lot of it stays locked up in solids, just in the matrix of the solids. It's mud. And then over time, especially as you pile more solids on top and increase the weight and thus the pore pressure, a lot of that water gets expelled and comes back to the pool. And that's the water we draw on when we want to recycle water and use it in processing. And there are a lot of factors. I won't go into them all, but there are a lot of factors all listed here, not all of them even listed here, that affect that. And, you know, some of the goals of some of the key selections is, well, what am I going to do to hasten that? Or what am I going to do to manage water? Do I get that consolidation early? Do I get it late? What's that mean for my water balance? And what's it mean for environmental performance? And the spot we landed here is what's called thickened, which is, again, that's in your 50% solids range. There are others, right? And they arrive at a different terminal number, but I didn't make that differentiate on the chart, but all of them get the water out sooner or later. We are at about a sweet spot on thickened, but other facilities, of course, make other choices with different tailings characteristics. Here's some examples of what they really look like, right? Conventional low density tailings, that can run 20%, 30% solids. That's the facility on the right. The one on the, I'm sorry, on the left, the one on the upper right with the box, that's where we are, thickened. So you see a little bit different consistency than maybe you're expecting to see, but we're not all the way to paste. We don't want to be there. We can't be there with the characteristics we have. And that's the one on the bottom where you're pumping toothpaste. And we can't pump toothpaste a couple miles up the river to that facility in our case. And then the bottom left is what one calls dry stack, where you actually run tailings through a filter press, which can get really energy intensive, of course, with finer tailings, which is kind of where we are. And it also works when it works, but when it doesn't, it really doesn't. And so again, thickened is where we landed here. And we still believe that's the sweet spot for our particular tailings and our particular site. And here's some of the outcome of that, right? We did consolidation testing on our tailings from our pilot metallurgy study. So this is really the full simulation of the full flow sheet of all of our ore processing here. And that led to a set of curves, you know, one on the wetter side, one on the drier side, or the faster and slower side of consolidation. And we picked a design curve in the middle. But in either case, these are set to be conservative intentionally with respect to sizing the facility. So we know we won't, you know, even if they underperform, we know we won't have a dam that's too small. We assume there's no bottom drainage, even though we'll have bottom drainage. When you do this analysis, you assume you don't. And so there's less path for the water to get out. The longer path, you're modeling it as taking longer than it probably really will, but that gives us some reassurance that even if it underperforms or even if drains clog, which can happen, that we know our dam is going to be big enough and that you won't be scurrying to expand it, which is a position some operators have found themselves in before. And it also is conservative with respect to water management and closure, because if you don't get the water early and your tailings stay low density, that means you're getting it at closure for treatment. And so this is also conservative with respect to sizing our treatment plant at closure. And then just all in all, I covered mainly consolidation, but there's other considerations, right? And where our tailings go, right? We have in our ore process, and we start with flotation after everything's ground up and in a slurry. We start with what's called flotation, which is how you get the sulfides out. And the sulfides that we skim off from flotation are what goes through the autoclave, which is called pressure oxidation. And pressure oxidation tails aren't known for their great settling characteristics, but most of our tailings are actually the flotation tail. The pressure oxidation tail is only, 10% of the total. And between that limestone we've added, and the fact that we're actually on the coarse side as gold tailings go at 85 microns of grind, they consolidate pretty well. And that means we have a decent confidence in those consolidation curves and that we get them consolidated quickly and we can close quickly and get water recovery for operations during operations. The other thing is between the limestone addition and the need to use the reclaimed water, we can't allow high cyanide levels in our tailings. Our cyanide needs to be 50 ppm under the International Cyanide Code, which we will comply. But we really need to be well south of 10, and will be, because we need that water back. And I mentioned flotation. Well, cyanide in your flotation water inhibits your recovery. So we've got very good reasons in gold recovery numbers to keep that cyanide very low in the tailings facility and in the water that returns from it. So we'll be far less than 10 ppm generally in the tails. And again, our pH is alkaline. There's no ARD in the tails. So from a standpoint of toxicity, pH, cyanide or arsenic levels, our tailings are good as precious metal tailings go, and consolidate rather well. So it's a manageable risk, and it's one we've accounted for in our design here. And then why I skipped it, move this slide down, because this is the water balance slide. This looks like that the same information as before, is one can't have a water balance without knowing the consolidation, because the consolidation of tailings and the entrainment of water with tailings and the recycle back from tailings are very large components of the site water balance. And these are some typical results you see with that. We look at different curves. How sensitive is it to the performance of the consolidation? What's that mean for scheduling of when your dam gets raised, and what's it mean for water availability? And what we saw is that we do pretty well here. We have a pretty controllable pool. That middle right you see is actually when we have to do some evaporation on a typical analysis. We'll see the need for some forced evaporation, but pretty minor midlife to control some of the pool seasonally. But generally, we do pretty well controlling the pool, and we get pretty good tailings consolidation performance. And now I'll pause now, because then we're going into geotech. So, anything, Shelley?
Nope, we're still good.
All right. Okay. Well, on to geotech, and this is one where I'll have a hard way and an easy way here to explain this. So, factor of safety is really it's just a ratio. It's just math of, well, what's the design strength of something, or what are the forces that tend to make it stay where you want it, and what are the forces that tend to make it go somewhere you don't? What's the stress versus the strength, or what's the stabilizing to the destabilizing forces? And we look at that at a bunch of different scenarios. Here, I'll focus really on the dam face, the downstream dam, and the sort of failure that would lead one to have the failure surface breach the dam and intersect the liner and lead to a release of tailings and water. There are, of course, again, we books worth of analysis here that'll get in with permitting, but this is the one that I think is the one to focus on, because it's the one that would imply, if it happened, a bad failure. So what stabilizes a dam, right, is how strong is it? What's the shear strength internally of it? Is it made out of clay? Is it made out of rock fill? How strong is the foundation? Is it sitting on rocks, or sitting on clay, or sitting on bedrock? And if there's a buttress in front of it, well, what's that weigh? And does that buttress help it a lot or a little? And then what will hurt a dam, right, of course, is the self-weight of that dam. Okay, great, it's strong, but it's also heavy, and heavy works against you. Is there seepage through it? Does it have elevated pore pressure inside it? That doesn't help either. And then shaking due to an earthquake, especially in combination with having high pore pressures. And we'll leave the earthquake thing alone briefly here for this next example, because a simpler way here, say, I want to make a chair. Well, what makes a chair strong, right? How strong are the legs? How strong is the floor? I mean, you put a chair in your backyard and sit on it, sometimes it punches into the earth, right? It's wet. If you put it on the kitchen floor, you usually don't break the floor. You break the chair first. So we're going to ignore the floor, but look at the strength of a chair just on its legs. Well, what else happens, right? What hurts a chair? How much does it weigh? Chairs don't usually break under their own weight, one hopes, but sometimes they break under the weight of their occupants. And here's your loading conditions, right? One person, if you take a chair and you say, I made the chair strong enough to hold 600 pounds. That's my base case, right? One person, 200-pound person on a 600-pound strength chair, the factor of safety is 3. Okay, Thanksgiving happens, gain 20 pounds. Factor safety is still pretty solid, 2.7. Lean back on 2 legs. Mom said never to do that. Well, here's why. Your factor safety is 1.36 now. Or hey, a lot of family, extra family came over before Thanksgiving and you shared your chair with your cousin, weighs the same as you. Factor safety is 1.5, still all right. Okay, well, what if you lean back then? Well, 0.7, below 1. 1 is incipient failure, right? So you both crash to the floor and somebody goes to the ER is what happens. So what would that mean for designing a chair to work under all these kind of loading conditions? 1.5, good advice, right? That's our criteria for a dam or minimum. That would mean that chair, if 1.5 under the loading condition of 2 of you leaning back on it, that chair should be able to hold 1,300 pounds capacity. And that would put that at a 1.5 under that bad loading condition there. So that's a little, hopefully better, easier to understand way to talk about factors of safety. Then last one, and we'll jump into Stibnite detail after this one, but closure considerations, right? You know, how active of a closure will you have? I mean, is it water treatment forever? Is it water treatment for 5 years? Is it water treatment for 10? Is it going to be vegetated? Will it be covered in rocks? Is it going to be covered with geosynthetics? And do you just leave, or will you be tweaking that design or tweaking that site and monitoring it for decades? And then will that be the same all throughout, right? I mean, in our case, it's early closure. It'll look like a lot of attention because early closure, we got to treat, get rid of the rest of the water. But late closure, it will be a bare minimum maintenance because we're planning a self-sustaining system out there. But so it's all, again, phased and more active earlier and less active later is generally where you want to be. And that's where we're trying to head. And then that's the general ones. And Shelley, last chance, and then I'm going to dive into Stibnite specific stuff.
Excellent. I would say go ahead and dive away.
All right, dive on. So design criteria, right? You know, those are a consequence, a lot of hazard classification and a consequence of what your tailings are. In our case, we're a cyanidation facility, of course, because we're precious metals. So Idaho has rules for ore processing by cyanidation. They, of course, also have dam safety rules. And so our liner system, our water management, those sorts of things mostly relate to the cyanidation rules. Of course, the pool management and freeboard has to do with dam safety. And then, of course, embankment stability touched by both rules. And then down the line, of course, we have water quality rules that come into play more at closure because that's when we'll actually treat for discharge. We'll be operating as a zero discharge facility during operations. We recycle all the available water. So where that gets us, though, is, you know, our static factor of safety, I mentioned before, has got to be 1.5. The one for earthquake's got to be a 1.0. And that's an analysis I won't dwell on because we're also well above it, as you'll see from just looking at the static numbers. And our design earthquake, again, we're what would be called a large high hazard dam, not because a failure is likely, but because the consequences should a failure happen are high, would be classified as high hazard under the state's classification. So our design earthquake is the maximum credible earthquake, which is basically the worst earthquake that could possibly happen at site, as opposed to some number like a 500 year or something. The MC is about a 10,000 year. They line up pretty well. So that's where we'd be. On the hydrology side, again, we're a large high hazard dam. So the biggest precipitation that it could occur on the watershed is our freeboard criteria, our inflow design flood. So we can store the runoff from that PMP. It's called the PMF, probable maximum flood. So our design is to store that in the impoundment, assuming the diversions don't work. So we assume we take the whole watershed, which if an event like that size happens, is certainly possible. But our diversions themselves, those will be designed for the 100 years. So we can route the 100-year flood around the facility, no problem. And then on water quality, and a lot of this, again, driven by the cyanide rule, what would have been done anyway, given our tailings, is we have what's called a composite liner, which is a geosynthetic clay liner overlain by a geomembrane, which is state of the practice of this industry. And we'd have some overliner drainage installed as well to try to keep the pore pressures down in tailings, keep the head off the liner. And then I've gone before I mentioned, we have neutralizing the tailings, we're detoxifying them, killing the cyanide down well below 10 ppm. So there's some efforts at the mill made to keep what goes to the tailings facility lower risk. And then I'll go into the geotech side here on how far ahead we really get on the geotech. So here's where we are. This is the global portfolio right here. This is out of tailings and mine waste a couple of years ago. This is a global portfolio of tailings facilities. And this is what a factor of safety really means. Factor of safety, again, is just math. It's just the ratio of forces. But doubling the factor of safety doesn't have the risk. You can increase your factor of safety. Your failure probability can reduce by factors of thousands. And you see here, I know the numbers are a little hard, but if you're at a 1.5, you're at 1 in 10,000 annual failure risk or so. And that's the standard, right? Idaho standards 1.5 static. Well, if you're at what we were at in the draft EIS design, which has been advanced a little and is actually better now, where we were then with those factors of safety, we're at an annual risk of 1 in 10 million. And that's not us that determined that. That's what came out of the draft EIS from the Forest Services consultant. So we plot so far to the right, you're basically off the page here on failure risk and factor of safety. And that was, again, before some improvements that I'll get into in a second. So it's, again, a dramatic change. When you double a factor of safety, you're not cutting risk in half, you're cutting it by orders of magnitude. And here's why we are where we are, right? This is our starter dam for our latest design, right? And the starter dam is the dam that's got to last you 3 years. And this dam, it's 200 some feet high, but it gets buttressed relatively early after it's constructed. And we've designed it so that it meets the required factor of safety without a buttress. So this thing's got standalone a 2. So we're 0.6 above the minimum. And that's unbuttressed. And the consequence of our updated mine plan is that it gets buttressed before it gets tailings. And I'll go through this phasing in a second here. So it gets buttressed before it ever sees tailings. The only thing in there is our water pool that we've accumulated for startup water from the mill. And that's far below the crest. That's going to be 40 feet of water or something like that, and consumed very quickly because it's for startup. So that's the initial condition. The final dam, we analyzed that for standalone as well, right? So that sits there standing alone, full height, never. It's a hypothetical case because, again, the buttress started before there were even tailings installed. So if that were a standalone dam, it'd be 1.8, beats the minimum by 0.3. So it's close to the standard, but over. So it exceeds what it has to do. But when the buttress is there, and this is the buttress, this is the full build out buttress, but it's pretty substantial before this point. The full build out buttress, our factor of safety goes up to close to 6 now. And that's again a consequence of reconfiguring the buttress a little, making it bigger and sooner than what we had before. So at all stages, we're buttressed. We have a standalone dam that exceeds the minimum in its own right, even if it stood alone, but it never really stands alone. There's always some amount of buttress there. And that always gets us at any stage to at least double. So double would be 3. And here we're approaching quadruple the design factor of safety, which again that's not 1/4 of the risk. That's orders and orders of magnitude of less risk. So again, we're already at 1 in 10 million here. Now it's probably better than that. And here's the configuration, just a different shot of this, right? Is a summary of the design, right? Again, I've beat you over the head with the idea of the buttress here. It's a rock-filled dam with downstream raises. We've got composite liner, we've got surface water diversion, got under drains, and we've got pore pressure relief. We really think we've covered all the bases here on what do you do to keep the water and geotechnical risks as low as you can. And here's again how it looks over time, right? Everybody we get a lot of questions as well. Okay, it's buttressed, that's permanent, but what about year two? Entirely reasonable question, right? The way it works now, the color coding here is that if it's a bright color, it's what's installed that year. And if it's gray, it was already put there. So, -1, that's our construction, our final construction year. You see end of -1, we've already got a buttress starting to grow. It's a modest one, but it's starting. You get into year one, you've got a substantial buttress on the stage two dam, and the stage 2 dam is already there. By year 3, which is when the stage 2 facility goes into operation, that is, tailings are starting to come up to the level of where you're past stage 1. By that point, you've got a very substantial buttress that's only growing more. You've actually got much of the facility already built to ultimate by that point. So it all acts as buttress. So what that means is this thing's quite a bit ahead of what is needed. And that's the consequence of some mine plan changes that move around where we put rock. And you'll see this little ladder chart, that's your picture of what your dam must be versus what your dam is, because you build it in discrete years and the tailings grow every day, right? So what that means is that during any given time, your dam's larger than it would have to be to control to store your flood. That flood is only met right at the end of the stage when the next stage is almost ready to be done. So your exposure window's, months. And then outside that, you could store multiples of that flood. So what that means though is, and here it is growing again, what you'll see here is year 5, we've got our ultimate dam. The only thing left to do in year 5 for subsequent raises related to the dam as opposed to the buttress, which grows more, the only thing left to do is put in some liner bedding and install your liner. So what that means is that we can stay ahead comfortably of our accumulated tailings in the water. And if anything goes wrong, which again, it shouldn't, but we have the flexibility to get a raise done on relatively short notice. We find densities aren't what we thought, we have a lot of flexibility to adapt because we don't have to spend time building a dam out of rocks we don't have, because the pits have provided so much rock early. We've got this thing built out. Most of the work is done. It's the detailed work, the contractor work that will be remaining, but all the mine fleet work is really done by year 5. We'll be at ultimate at that time. And then as far as where it goes after that, right, is the final closure plan. I think many of you probably heard before, but right, Meadow Creek will go back. Right now it'd be routed around at the end of operations. We will treat water to get rid of the consolidation water once the tailings have consolidated, such that they're not making so much more water and such that we can get out on the surface, drive around and place things that will stay where we place them and not settle too much. So once we've reached, pretty high level of consolidation, we put back the river, we put back the wetlands. That put back is really a lined corridor above the tailings, and it's got, 5 or so feet, varies, but several feet of material above a liner, isolating all that consolidation water that remains, which again, a lot of it's gone by that point, but isolating the consolidation water from the stream and allowing a stream corridor that really can act like a stream corridor. The material going back in on there is not riprap. It's going to be floodplain material, and it's going to have vegetation, and it's going to be a stream corridor that can do what streams want to do over the long term. And so where this brings me here is going right back to risk analysis or risk. Here's our risk ratings, or how we see them pre-mitigation, right? We're orange: climate, hydrology, foundations, topography, right? Those are the orange ones. And then we've got some yellow ones there. And we've done all we can to study those and analyze those and come up with mitigation measures. And all of those I've covered, right? We've got a large freeboard. We've got full diversion of surface water. We've got close to 100 holes of geotech, as well as a lot of analysis and investigations. And then we've got when it all comes down to it, we've got a buttress of 80 million tons of rock that stays and keeps this thing stable. And then we've got, of course, on the water quality side, changes to the process. And then with that buttress and with how fast that thing grows in there, we've got a lot of slop in the timeline to adapt if anything does happen. And where that brings us is this, a lot of the orange becomes yellow or green, and a lot of the yellow becomes green on this chart once you take into account what we've done to keep our risks down. And where that gets us is, no facility that's got a buttress like this and that is a rock fill, aligned rock fill with downstream raises, we know of no such failures. There have been failures of facilities that are downstream. There have been of each individual of these things, sure. But if something that has all of these, none that we know of. And so that's it. And this is a summary slide. I've said it 3 times, so you folks can read it if they want, but I think we can go to questions.
Thank you very much, Gene. We have a few questions. So the first one I wanted to ask you is, what are the regulatory agencies governing the facility design, and what is included in the third-party TSF review?
Okay, so the regulatory agencies governing the design, that is the established design criteria, it's really the state of Idaho, because through the cyanidation rule and through their dam safety rule, there really aren't any criteria overhead of that exceed that. Those criteria are basically state of the practice. International Commission on Large Dams matches that. CDA would match that. Our federal standards all pretty much match that. So the controlling criteria is state, but it's in harmony with numerous others. And then I've already forgotten the second half. So what's the second half question?
No problem at all. What's included in the third-party tailings facility review?
It's a comprehensive review of the design. So it's design criteria, the geotech analysis, the hydrology. It just have a peek at the design, at this point, have a peek at the design documents. Now, as we go forward, that will also include looking at the geotechnical monitoring and all the monitoring, I mean, the water balance too. As we go forward, actually build the facility, it will be looking at the construction practices of instruction QC, and then as we operate the facility, it would entail all the monitoring data, the operational monitoring data of the facility too. So the third-party reviewer has access to all that. It's just that at the phase we're at, they're looking at the geotech investigations that we've done, and the conclusions of those, and the geotech analysis we've done, and hey, did we pick the right soil strength based on the geotech investigations, or did we overestimate the strength of that soil, whatever. So it's a comprehensive deep dive at all of what we have. It's just that then there's more, like subsequent stages would have more and more data for them to look at.
Excellent, thank you. I'm looking at the site today. Are any of the legacy tailings at the site lined, and what will happen to tailings if the project moves forward?
No, the legacy's tailings are not lined. They were deposited right on the river bottom. They did have water diversions, several actually, they were moved around. They're actually draining dirty water into the creek presently. So the existing tailings sit there unlined, and they have spent ore on top of them. The spent ore is not necessarily benign either. And so they're all just sitting out there, and they're leaching metals, and it's ending up ultimately in the creek. And the plan for that is right, the SODA, the spent ore disposal area, as well as the heap leach facilities to the east. We're gonna pick them up, use them as construction material, but we plan to use them up high and dry, so they won't ever sit in the valley bottom. We have them up above in the dam and in the fill associated with it. And then over top of that goes our liner, more or less right after. So they would be high and dry and underneath the liner. And then of course the liner would be overlain by tailings that as they consolidate become pretty tight in their own right. So you're looking at a permanent isolation from meteoric water and groundwater for the spent ore. The tailings we will pick up, reprocess with our own ore. And so they will end up in the tailings facility with all of our own ore. And they are no different at that point than ours, right? They were ground a little coarser that we will grind, and they did get decent recovery, but there remains some metal in there to recover. So they'll get the end product of those. They'll be indistinguishable and mixed with our own tailings in the engineered facility that's fully lined.
Okay, And will our tailings facility be dewatered post-closure?
Yes, well, it'll be dewatered in that we will pull off and treat all the water from the surface. So the consolidation water. Once that's gone, you're limited to what runs across the cover, right? At that point, you're stabilized it, you've covered it. And what remains at that point is the tailings deposit underneath the cover. That will be saturated at depth, but it will be saturated in the same way that soil below the groundwater table is. There won't be excess pore pressure anymore, but it's unavoidable that it be saturated if you're to have a lined facility. But it won't be interacting with any water. It won't be going anywhere.
Okay. And will this is a question from one of the gentlemen we know, is the embankment raise outer shell filter compatible with the buttress fill?
The embankment raise in the outer, the embankment raised in the buttress are simultaneous, and there's really a point where they're indistinguishable. They're a line on a cross section, but they grow together. You know, the buttress and the dam are coming up together. There are different zones within them. So everything upstream of the crest of the dam has got a more stringent compaction specification and a thinner lift height. So the buttress will be at 50-foot lifts or whatever it is as a buttress. In the dam, in the dam upstream of the crest, your lift thicknesses get progressively thinner and your compaction specifications get progressively more stringent as you approach the liner. And the liner will have a transition fill that again, this is why we use contractors for the upstream face, because you've got to pack the liner bedding in, get a firm subgrade for the liner, and get a perfect subgrade with nothing sticking out that's pointy that could hurt the liner. You do all that on the upstream face with contractors. The stuff downstream of the crest corner basically it'll stick up sometimes, but it's once the part that's not sticking up above the buttress is just a dotted line on a cross section. It's the same lift thickness and it's indistinguishable from the buttress. Because all it has to do all that part has to do to work is be there and be heavy. You know, that part is just bulk fill. It doesn't require any special treatment of any kind.
Perfect, thank you. So we're nearing the 1 o'clock hour, so I'm gonna go ahead and give you one last question to close out. I've had a few people ask, if this project does move forward and get permitted for construction, what scope of work would we hire out to outside contractors and what would we keep inside?
For the starter dam, almost everything would be outside contractors. The mine fleet would deliver the bulk fill that originates from the pits or from removing the Hecla heap leach, which lies to the east there. And it's one of the early sources of reuse material. So basically the mine fleet's going to be delivering to the dam site, but really all the work is contractor work for the early build. So delivery of material by the mine fleet, you know, load, haul, dump, contractor would be spreading and compacting a lot of that stuff until it came up a little bit. You know, you get into the end of -1, then your mine fleet will be doing more of the dam fill. But again, most of the work and all the value added difficult work, the high specific, high spec work is all contractor work. It's all the fine earthworks, the stripping, the diversions, and the liner installation, of course, is a specialty contractor.
Excellent. Well, thank you so much, Gene. I think that we've had a lot of education today on our tailings storage facility. And thank you everybody for joining us. I really appreciate you taking an hour out of your day to learn more about the Stibnite Gold Project. We do give webinars quite frequently, at least once a month, if not more. And you can find all of our webinars to register for at this website that you see on your screen. So with that, thank you very much, Gene. Thank you all for attending, and I hope you have a wonderful day.
Yes, thanks everyone for listening.